Welcome to a new lesson. In this lesson, we'll be using reasoning to find a counterexample to a conjecture. Let's first define what a counterexample is. A counterexample is an example that makes a conjecture invalid or false. Let's use this definition in the next example. In this example, gather more evidence to test Carey's conjecture. Carey created a series of circles. Each circle had points marked on its circumference and jointed by chords. As the number of points on the circumferences increased, Carey noticed a pattern for the number of regions created by the chords. So let's talk about these circles. Let's take a look at the first circle. Carey noticed that if she put 2 points on a circle and connected the circle with a line, 2 regions were created, 1 and 2, on a circle. Now in the second picture she noticed, now she used 3 points on a circle and had 3 chords connected. When she did that, she noticed there are 1, 2, 3, and 4 regions created by this. The next picture, she joined 4 points, and she noticed that there are 1, 2, 3, 4, 5, 6, 7, 8 regions. Then let's make a table to see clearly the relationships between the circle's points, the circumference circle points, and the regions created by them. So here's the table. Number of points, 2, 3, 4, 5, 6, 7 on the circle, and the number of regions. In the first picture, we see that there are 2 regions. In the second picture, when we have 3 points, we have 4 regions, and in the third picture, when we have 4 points, we have 8 regions. You could look at the pattern and see that there's something repetitive. Now, the pattern is that we are multiplying by 2. So the next pattern would tell us that at 5 dots on the circle, we'll have 8 times 2, which is 16. And then we'll double it again to get 32, and double it again to get 64. Double it again. Based on this pattern, we can come up with a conjecture. As the number of connected points on the circle increases by 1, the number of regions inside the circle doubles. Based on this pattern, this is our conjecture. In order to prove our conjecture, we have to use inductive reasoning, and in this inductive reasoning, we will have to draw the next circles to see that indeed we will get 16 and 32 when we have 5 circles, 5 dots on the circle, or 6 dots on the circle. So let's draw this shape. Here are 5 points in a circle. We're going to connect all the points together. And we're going to count the regions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So recall the table. It told us that at 2 points in a circle, we'll have 2 regions, and we had 4 regions, and we had 8 regions, and at 5 we would have 16. And from the picture, as you could see, there are 16 regions when we have 5 points in a circle. Therefore, so it's correct. It does check out. What about for 6 points in a circle? Let's draw that picture. So here's the beginning of the picture. Here are your 6 points, and now we're going to connect all the points together. So here's the picture. Now we're going to count the regions. We can start in the middle, because that's one's hard to see. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Remember, we're looking for 32. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Is there any more? No, that's it. So now we had to have 32 for 6 dots on the circle, but really it turned out that 31 is what we get. Therefore, this is the counterexample, and our conjecture is invalid. So our conjecture is invalid. 6 points on a circle make 31 regions and not 32 regions. Let's take a look at another example. In this example, Stefan's conjecture, the difference between consecutive perfect squares is always an odd number. Francisca's conjecture is that the difference between a consecutive perfect square is always a prime number. How can these conjectures be tested? Before we write the conjecture, let's define what is a perfect square and what's an odd number. And of course, what's the difference? The difference has a mathematical operation of subtraction. The word consecutive means next, such as 1, 2, 3, 4, 5. They're all consecutive numbers. Next, 1 is next to 2, 2 is next to 3, and 3 is next to 4. And odd numbers are numbers that end with 1, 3, 5, 7, and 9. Also, what is a prime number? A prime number is a number that is only divisible by 1 or itself. Here's a list of prime numbers: 2, 3, 5, 7, 11, 13, and so on. 9 is not a prime number, for example, because it can be divided by 3. So 9 is not prime, not a prime. Let's use this information to come up with a conjecture. So let's first find a pattern using inductive reasoning, so that we're going to be putting values into this problem. So let's use the first consecutive prime numbers. There are squares. Now, a perfect square is basically squaring an integer. So for example, 2 squared. The consecutive value from 2 is 1. So 2 squared minus 1 squared is 3. The next consecutive ones is 3 squared. And 2 is next to 3, so it's also consecutive. 3 squared minus 2 squared is 5. 4 squared minus 3 squared is another example, that's 7. And 5 squared minus 4 squared is 9. That's the other number we're going to be using. Now, notice what Stefan's conjecture was. Stefan's conjecture was that the result of all the difference between perfect squares that are consecutive is odd value. If you look, these are all odd values. the one at least we chose. The pattern, as you could probably see, is increased by 2. That means that the patterns will continue. It'll always be an odd value. So I believe that Stephan's conjecture is true. And the reason why Stephan's conjecture is true is because I cannot find a counterexample. So again, Stephan's conjecture is valid because there is no counterexample. Now let's take a look at Francesca's conjectures. Now it's the same pattern, so it is still consecutive perfect squares, but now she says that the result will be a prime number. As long as we find out one counterexample that shows a prime number as a result, then Francesca's conjecture is invalid. We'll take a look. 9 is prime. Because earlier we could take 9, divide by 3, and since it is divisible by a different value than 1 and itself, it's a prime number. Because there's one counterexample, her conjecture is invalid. So again, Francesca's conjecture is invalid because 5 squared minus 4 squared is 9, and 9 is a prime number. That's the counterexample. Let's take a look at one more example. Matt found an interesting number pattern. 1 times 8 plus 1 is 9. 1, 2, or 12 times 8 plus 2 is 9, 8. 1, 2, 3 times 8 plus 3 is 9, 8, 7. 1, 2, 3, 4 times 8 plus 4 is 9, 8, 7, 6. Matt thinks that this pattern will continue. Search for a counterexample to Matt's conjecture. Now, before we jump into this question, let's define or compare the idea of numbers versus digits. A digit is composed of numbers that are between 0 and 9. So 0, 1, 2, 3, 4, 5, 7, 8, 9. A number, it can compose one or more digits. For example, a number of 239 has a 2, 3, and 9. It has 3 digits, a 2, 3, 9. So let's take a look at Matt's pattern. Let's continue the pattern before we make a conjecture. So notice that the pattern is that we increase another digit, we put another digit to the end of a number, and that digit increases by a factor of 1. Not really a factor by addition of 1. So we have 1, then we have 1, 2, 1, 2, 3, 1, 2, 3, 4. So the next number will have 1, 2, 3, 4, 5. Then we're still multiplying with 8. And in this case, the next number increases by 1. We have 1, 2, 3, and 4. The next value we add in is 5. And apparently our result numbers will have an increase of one more digit. So we have 9, 8, and that digit decreases by 1. 9, 8, 7, 9, 8, 7, 6. So we have 9, 8, 7, 6, 5 as the answer. So we continue the pattern 1, 2, 3, 4, 5. Now we increase to one more, which is 6. We still multiply by 8. We add that 6 again. And now we have 9, 8, 7, 6, 5. And we increase one more digit. And that digit is by 1 less. We could keep going with the pattern. And here's the pattern. We finish off at 1, 2, 3, 4, 5, 6, 7, 8, 9 times 8 plus 6 equals 9, 8, 7, 6, 5, 4, 3, 2, and 1. In order for this pattern to continue, we have to choose the next number. Now, let's get back to this question. Make sure you don't make minor mistakes like I did. It's we increase by 7, then by 8, then by 9, and not just by 6s. So make sure you don't make that mistake. So the problem is that now that 9 has to be changed. Now, is it going to be changed to a 10, or is it going to be changed to a 0? That is the question. So there are 4 different combinations that we can try to find out if this pattern continues. Here are the combinations. Suppose the increase is by digits, and that the next digit after 9 should be 0. So we're going to multiply by 8 and then add this 0. The result is 9, 8, 7, 6, 5, 4, 3, 1, 2, and 0, not 2, 1, 0. Therefore, this is a counterexample. It doesn't work. What if this is not a digit by a number? So after 9, the next number is 10. Times 8 plus 10. Our result is 9, 8, 7, 6, 5, 4, 3, 1, 2, 9, 0. But we're expecting 4, 3, 2, 1, 0. So this is also a counterexample. It doesn't work for us. Well, what if it's a combination between 10 and 0 for the next try? What if it's a 0, because the next digit after 9 is 0, but really it is addition of 10? And the answer is 9, 8, 7, 6, 5, 4, 3, 1, 3, 0, not 3, 2, 1, 0. So again, it doesn't work. And the last chance is that what if really it's a 10 here and we're adding a 0? Our result, so the result is 9, 8, 7, 6, 5, 4, 3, 1, 2, 8, 0. So again, the pattern doesn't hold for any of the values once we passed 9. Again, how are we getting these values? 9 is by calculator. We're plugging it into your calculator and finding these values. So the pattern doesn't continue past the digit 9. And the counterexample to this example is the digit 0 or 10.